I have to go 10 minutes.
Good? Morning, guys.
Good morning.
That sounds so enthusiastic for more immunology on a rainy Thursday. I must say, I've taught this class to PA students for Arcadia for years, and I am terrified today. And the reason I'm terrified is I've been told I have to stand on this piece of plastic, and if I wander off it, I give the people in Glenside vertigo or something. And I pace like crazy. So we're going to have to see, because by the end of an hour, if I start like babbling, it's simply because I can't walk and talk at the same time. So we'll see if this works. So a couple things just as a prelude. I understand. Congratulations, by the way, for getting into PA school. Not an easy thing to do. So tipping my hat off to you guys for doing that. Sorry for all my crap right over there. Is that okay? Yeah. Don't mind just you push it on the floor.
No.
I also understand that this is the end of your immunology section, right? And what I'm going to be providing to you today is an introduction to immunology. I am not responsible for the timing of this. So if this seems a little backwards to you, that's not on me. But I think this might be helpful for you guys, because I'm told that you don't have to take notes for this. I think that's right. Is that right? I certainly don't test you on this stuff. They've never asked me for test questions. So what might be useful here is that I have no idea what you've been taught already. But what this might be useful for is reinforcing some of the things that you learned in preparation for the test. When do you have a test? Okay. So I think did I go off? Am I okay? Okay. You're going to have to endure 2 hours of me being insecure, so suck it up. That's how it's going to go. All right, so what do we want to accomplish over the next 2 hours? This is going to, first I'll introduce you to me. This will be the only time in your entire PA career that you see me. Hopefully we'll never encounter each other as caregiver and patient. So this is one and done for you, so I'll tell you who I am. And then we'll underscore the reasons why you hate immunology, because you know you do. You're happy that the session is over. You're like, really, one more, another guy teaching us immunology. So we'll talk a little bit about the justifiable reasons why you despise this field. Then we'll talk about what I believe are the core principles of the host immune response. And we're going to put into context what I suspect are some of the themes that you heard about over the last, 4-hour lectures? Is this right? 4 hours? I can't sit through 4 hours of anything. How do you guys? Well, all right. Then we'll focus on how the immune response might contribute to human disease, with a particular focus on virus infections, because that's what I do. We'll talk a little bit about vaccines, because they asked me to, and then we're going to end in a weird place. And the place that we're going to end is actually not talking so much about science at all, but about how you interact with patients, particularly parents of kids that might be your patients. And we're going to talk a little bit about vaccines and autism and about your responsibilities as frontline caregivers. And it's important that we do this, because I suspect that this might not be part of what you guys are taught as future physician assistants. And so for us to spend, 20 minutes talking about this at the very end might be an interesting little coda to your series of lectures on immunology. All right, does that make sense? Please, I'm a super informal fellow, so feel free to interrupt me if I don't make sense or if I start to babble. I have no idea. Hello, Glenside. I actually drove all the way down here, but I live about 2 minutes away from where you guys are. I'm not sure why I'm down here. But in any case, hello to folks near my home. All right. So who is this guy and why you hate immunology? So this sounds a little grandstandy. My apologies if that's true. I am a professor at the Fox Chase Cancer Center in Philadelphia. Been there for ever, probably about when you were 3 years old, right? Somewhere around there. I'm an adjunct professor at lots of different places in the Philadelphia area. My lab is interested in virus infections and immunity in the central nervous system. Fret not, we're not going to talk about any of that stuff. Purely grandstanding, I am the co-author of this textbook called Principles of Virology, and I'm pointing this out for two reasons. One is that some of the figures that I'm going to be showing you in this lecture, and by the way, did you get my slides?
Yeah.
Yes, good. You didn't get all of my slides. There are some because I want to keep you kind of with me and awake. So there are some slides that I omitted from here. I'm more than happy to send you my whole slide deck, or I can give it to Megan, or however we want to do this, so you have the full set of them at the end. There's only a few that are missing, but don't fret if all of a sudden I'm showing you a slide you don't have in your deck. The other reason why I'm showing you this, in addition to the fact that I'm using some of the figures from this, is that it's, where is my thing here? It's only 180 days till Christmas, and this would make a lovely Christmas gift. So bear that in mind. Okay. So raise your hands. No one else will be able to see you. Raise your hands if you actually despise the field of immunology. Okay. And you're not just telling me that, right? Some of you are like, oh yes, my hand is all the way up. I hate this field. In the back, she is enthusiastically. And you're right to hate it. So let's talk about the reasons why you do, and then let's try and detangle some of those things and make it make some sense. So first of all, especially if this is new to you, did you guys have immunology as undergraduates? Any of you guys have immunology? Some of you did? Okay. So not all of you. So it was probably a cold splash of water when you started talking about MHCs and TCRs and haplotypes and genotypes and all the rest. And it is particularly challenging because immunology, like probably any discipline, is a new language, but in particular, it's hard for immunology, right? So I picked at random, no lie, I picked at random from the Journal of Immunology, this is a couple years ago, a random article, and there is the title of the article, right? Nothing about this title makes you actually want to read this article. This is the most unwelcoming title that you can possibly imagine because you have no idea what any of these things mean, right? But to immunologists, this has content, but if you try and now teach it or convey it to someone, it's a little bit meaningless. There are other more substantive reasons why you don't perhaps like the field. It's dynamic. So everything interacts with everything else, and all components of the immune response or the immune system are equally important. So it's difficult to establish a foundation for how we talk about how all of these different moving pieces interface with each other. Right? So this is actually a figure from my text, which will guarantee that you will not purchase it. But this, don't worry, you're not responsible for this, but this is actually a figure from the text where you look at something like this, right? So how something happens inside a cell with all of these different green arrows, and you look at this and you're like, this is so ridiculously complex that you're just like, screw it. I don't want to pay attention to this. And yet, and this is sort of the point of this lecture, and yet there are principles that guide the details, right? And in this particular figure, the whole point of this is simply to say, when a virus binds to the outside of a cell, it does all sorts of intersecting and overlapping things within that cell that ultimately result in the synthesis of one protein called interferon. And those interferons are important. Right? So it doesn't make it easier to understand this stuff if, in fact, you were responsible for understanding this stuff. But at least it provides a bit of context to it, right? So that you understand, all right, what's the whole reason for doing all this, as opposed to trying to memorize all of the different players and factors. The third thing that makes immunology, I think, hard is that it's all throughout the body. Right, so unlike the central nervous system or the digestive system or the reproductive system that has a sort of defined anatomy in place within the human body, the immune response has no home, right? It's in the spleen, it's lymph nodes, it's the thymus, it's the bone marrow. So it's actually very difficult if you open up a mouse, or if you open, which my lab does fairly frequently, to show where the immune response is. I can easily track the entire digestive system, but the immune response is kind of all over the place, right? But there's reasons why that's true. If you think about what the job of the immune response is, it's to keep you safe from all the other things out there that want to infect you and grow in you. And therefore, for the immune response to do that job effectively, it has to be on all of the surfaces of you that interface with the environment. Okay? So these are all the different ways that viruses, sorry, I'm getting over a cold. These are all the different ways that viruses can gain access to you, right? So obvious ways like the respiratory tract, like the common cold that I had last week, or the digestive tract. So if you eat something that is nasty or toxic, your genital tract, anus, through skin, so access to blood through skin, through the mouth, through the conjunctiva. So there's all different ways. And in fact, the immune response is present, or at least parts of the immune response are present at all of these sites as sentinels or guards to try and catch that infection early to alert your host immune response to minimize the duration of the disease that you suffer. Okay? And then finally, it does lots of things. So globally, the job of the immune response is to fight pathogens, bacteria and viruses and parasites and molds. But specifically, how it accomplishes this is through a variety of distinct processes, some of which are tailored to the nature of the pathogen, right? So we're going to use different strategies if we get rid of viruses than if we get rid of bacteria or parasites, okay? So those are the reasons why you hate it. Anybody want to add other reasons why you hate immunology? There may be many others. I don't know. No? Okay, that's fine. So let's play a game. Name some components. You just had five solid 4-hour lectures on immunology or something. So name some components of the host immune response. Don't be shy. Let's see. It always starts with one brave person who whispers. Go ahead. What? That's fine. Good. See? Safe. I'm not going to bark. Yeah, something else?
T cells.
Fine. Wow, we're pushing it. All right. Keep going. Yeah, here we go. Here come the brave ones. Now. Compliment. Fine. More.
Cytokines.
Yeah. Let's go. Keep going. I'm going to pester you until I get 3 more.
Potential killer cell.
There we are.
Plasma cells.
Plasma cells. Good. One more.
Basophils.
Okay.
Inflammation.
Exhausted. You're like, let's just keep on. Why is that? So you're right, but you're also terribly misguided, right? So you're all correct in terms of defining components of the adaptive and innate immune response. But look at the question. Name components of the host response, right? And this is what I wanted you to say. Things like skin and mucus and stomach acid and saliva and tears and scabs and defensins. Because 99% of the things that want to grow inside of you first are repelled by these things, right? That's the big secret. So immunology textbooks teach that it's all about basophils and T cells and B cells and macrophages and plasma cells and cytokines and all the rest. And those things are true. But before it ever hits any of those things, that virus, that bacteria, that parasite has to contend with this stuff, right? You are coated in this thick sort of keratinous layer of goo and slime and sticky mucus and stuff, all of which are there to repel the very things that want to grow inside of you. To neglect these things is to ignore one of the chief hallmarks of the host response to pathogens, okay? I would even argue, so that my co-authors didn't let me put this in here, but I would even argue that something like intuition is part of your host immune response, right? Tonight, after however many hours of classes you have to endure, you go home, you look in the refrigerator, there'll be something scary in the back, you think it may be Chinese food from last week, you take it out, you smell it, it smells horrid, you don't eat it. And that is good because there's something nasty growing in that, and if you were to eat it, you would get very sick. Your intuition says, don't eat that nasty stuff, which apparently is in your refrigerator. Did you?
Leftovers from a week ago. Yes.
You need to work on this.
I had intuition. Sorry, I knew.
We're proud of our intuition here. All right, but I think that point makes some sense, right? And so all of these things, right? So mucus is actually a remarkable feature. We're not going to spend much more time on it, but in addition to it kind of coating layers of all surface layers, right? So your whole digestive tract, your urogenital tract. In addition to that, it actually has proteins within it that actually glob onto and recognize pathogens when, like neutrophils, for example, that will recognize pathogens once they're kind of stuck to the flypaper that is the mucus that lines all of your tracts, right? So, like, this is just, you know, the power of a sneeze, so this is a particularly juicy fellow sneezing. This is the perfect way to transmit an infection, right? A sneeze range, if I was here last week, I'd be sneezing, and my sneeze range would be able to reach you guys back there. The little particles, as disgusting as that sounds, the smaller they are, the longer they're able to float in air. And even one of those little particles, any guess how many virus particles, let's say the common cold or influenza, can fit into one of those little micro droplets that you can't even see in the air? Any guess? It's between 100 and 500 million virus particles, right? So you are constantly, you as a human, you as an organism, are constantly, your patients are constantly bombarded by things in the atmosphere all the time. And yet what? You get sick 3, 4, 5 times a year at most, right? So all of these features that we referred to are kind of the unheralded heroes of the host response. And because they're not, you know, TCR rearrangements and all the complex VDJ recombination pathways that no doubt you've talked about, even though they're a little bit more kind of brute force gross anatomy, they're nevertheless an important part of who you are and how your host response works. Okay, so indeed, then all the things that you said were accurate. If a pathogen is able to get past those initial physical barriers, then you actually trigger this whole cascade of potential events, right? So immediate responses that are made by the host are called intrinsic immune responses. Those include things like interferons, apoptosis, microRNAs, autophagy. Eventually, then the innate immune response kicks in. So somebody gave a shout out to natural killer cells and complement, antigen-presenting cells, neutrophils, and eventually, finally, you end up getting to the adaptive response. Now, the adaptive response is the most tailored and the most specific for the pathogen that you have or that you're trying to contend with. And so in that sense, it is the very specific, let's say, retinopathist, right? The guy that is only focused on studying the retina. But you actually have to see the eye doctor and maybe your primary care physician or your PA before you would end up getting to that level of precision, right? It takes hours to days, actually, arguably not hours, days, to trigger the adaptive immune response. But once you get there, now you've got the professionals on call. But you've got the immediate and innate, the intrinsic and innate immune responses that actually fill in the patch during that period of time while the adaptive immune response is generated. So you can think about it as in order for a pathogen to make you sick, and again, I'm a virologist, it's what I study, so most of the examples I'm going to give you are in the context of viruses. In order for a virus, bless you, in order for a virus, 3 to 6 feet, remember, in order for a virus to be able to make you sick, it's got to be able to leap past these various walls. And just to underscore it one last time, anatomical and chemical barriers are by far the thing that repel greater than 99-point-something% of the stuff that you would breathe in or be exposed to. Okay? Good? So far? Everything fine? All right. Hating immunology, maybe just a little bit less? Maybe just a little bit less? All right. So what are the core principles of the host response? So if I were to teach an immunology class from beginning to end, I could do this, right? I could start with teaching immunology one cell at a time, and we would spend today talking about neutrophils and what they do, and they're cool. And then we'd spend tomorrow talking about basophils. And then we'd talk about T cells, but of course we'd have to talk about how they're different from B cells and how receptors rearrange and what they recognize. So you could teach it like this. And I don't know, maybe you were taught like this. But a better way of thinking about it, just like we talked about that irreducible complexity of all of the different ways that a virus can trigger interferon signaling, a better way, I think, especially in this context when I only have 2 hours with you guys, is to come way, way, way out and think about what are the core cardinal things, the principles that an immune response has to do in order for it to work to your advantage. And this is just me. There may be other immunologists who would disagree with these principles or who might add other ones. But I think in its most reductionist sense, the immune response has 5 attributes or 5 characteristics. It is specific, it is diverse, it is fast, it has memory, and it is self-controlled. So we're going to take a break after, 40 minutes, but I want to kind of walk you through each of these principles. We're going to highlight some of the things that I think you've already heard about in this class, but we're going to put them into the context of these core principles. And then once we get to the end of that, we'll take a little bit of a break. We'll come back and talk about how the immune response can fail you, vaccines, and autism right at the very end. Okay? That's how we're going to go. So specificity. So let me just get all of this up, because it's lots of animation. So this is just an average tissue comprised of cells. If you happen to be infected with, let's say, the red virus, your body ultimately will make a red-specific immune response. Those are the T cells and antibody-producing B cells. And what will happen is that those red-specific immune cells will just get rid of the cells in your, let's say, lung that are infected with that virus, right? So very precise surgery to remove only the infected cells. And if at some point later you're infected with a different virus, the green virus, you now make a different immune response specific to that virus. It too clears out those cells. And ultimately, in general, with the exception of the brain where there's less cell renewal, but you end up being whole again after this because all of those places that the infected cells have been killed or cleared end up refilling because of cell division, right? So, and everybody is better. This actually is a huge issue where I work because this is the promise of immunotherapy. And as you guys become physicians, physician assistants, this is going to be something more and more that you're going to hear about or that actually might be part of the clinics in which you work, right? Because at Fox Chase, how do we take care of cancer? Like, what are the 3 ways that we take care of cancer? Chemo, radiation, surgery, right? So fairly brute force approaches, right? We cut it out of you. We zap it with radiation that has all sorts of unanticipated effects, right? Because it's zapping to the tissue, so there might be collateral damage to healthy tissue. Or the chemotherapy, which might be the most toxic of all, right? Where you lose all rapidly dividing cells, not just your hair cells, but also the immune cells that are actually important for fighting infections because they're rapidly dividing too. The strategies we use to treat cancer are pretty brute force. But what if we could actually take your host immune response and instead of using it to recognize a flu-infected lung cell, now use the host immune response to recognize cervical cancer. And have that host immune response, your own T cells, go in and only take out the cancer cells and leave all of the adjacent non-cancerous tissue intact. This is the whole promise of immunotherapy. And anybody that you talk to who works in a cancer discipline will talk about this as being the true new wave of cancer care. This is like the 4th leg of the cancer stool, right? And it's all about harnessing the specificity of the host immune response. So sorry for all the words, but I think this will be relevant to you here. So so obviously viruses aren't red and green. So how does a T cell know which cell is infected and which cell is not infected? And all of this should be summary to you guys, but all of your cells, every cell in your body, with maybe the exception of neurons in the central nervous system, but certainly lung cells and epithelial cells and hepatocytes and everything else, are constantly sampling the proteins that are inside of it, the host proteins that are inside of it, and putting little pieces of those proteins up on the surface of the cell. And those are presented in the context of something called class 1 MHC. Those little pieces of protein, your own host proteins, even if you're perfectly healthy right now, every single cell in your body is actively sort of sampling the different host proteins that your cells have and are kind of displaying them on the surface. Those little pieces, which are about 7 to 9 amino acids long, are called epitopes, right? And these epitopes aren't just little 7 to 9 amino acid pieces that are flung on the surface of the cell, but they're presented almost like a ball in a catcher's mitt in the context of something called major histocompatibility complex, or MHC, in this case, class 1. Okay? Is this familiar? Is this sounding familiar? Okay. And this MHC molecule is not just important as the presenter of these epitopes, but it's also something that your host immune response knows is you. Right? So this whole process, so it's called MHC restriction, which we're going to talk about in just a little bit more. But this MHC molecule is something that all of your T cells have learned, okay, that is me. I am, Lauren, and that is my MHC molecule. When that MHC molecule is now presenting something that isn't you, let's say a virus protein or a little virus epitope, now T cells recognize the difference, recognize that virus epitope, but present it in the context of self, right? So it's MHC plus now something new that the immune response hasn't recognized before. And that is the trigger for T cells to become activated and to work. So you're wondering what my midnight snack run analogy is. So imagine, I don't know if you have roommates, but let's imagine that in the middle of the night, pitch black, you get hungry and you want to walk to the refrigerator and not alert any of the other people who are living in your apartment. And so you have to navigate carefully your way, let's say, out of your bedroom, through the living room, through the dining room, into the kitchen to where the refrigerator is, and do this all silently to not wake up your neighbors. It's pitch black, but you know where all the furniture is, okay? So you can actually avoid all of those things. But what happens if right before you went to sleep, your roommate moved a chair? Now you're going to slam into that chair and you're going to scream, because it's going to hurt. And the reason why you're going to respond is because in the context of what is familiar, you've now recognized something that's different. There's something that's now a little bit different, and that causes you to become alerted. The same is the context in terms of a virus or a bacterial epitope presented in the context of MHC. Okay? So antiviral T cells see a particular pathogenic peptide or viral peptide in association with this self-MHC molecule, and it's this combination of familiar, your self-MHC, plus different, that foreign epitope, that's the trigger for the T cell to act. And that whole process is called antigen presentation, right? And it looks like this. So this is just a basic cell. Here's a target cell, and this could be any cell in your body. There's the nucleus up there that's making RNAs, and the box is the endoplasmic reticulum. So when you're infected with this virus, the virus comes in, and its job is to make more of itself, but in doing that, it has to make viral proteins, so it makes these 4 proteins. These proteins get degraded through something called the proteasome, and they get turned into these short epitopes, or these 9 to 11 amino acid peptides. Those are transported into the endoplasmic reticulum, where they meet with class 1 MHC and something called the light chain, which seems peripheral to what you need to know about, called beta-2 microglobulin. And once those 3 components are present within the ER, that then gives the signal for the MHC molecule to move to the cell surface, and that is what's recognized by the T cell receptor of a cytotoxic T lymphocyte, right? So that interaction right there is the fundamental way by which T cells become alerted to the presence of something foreign. Okay? And you're going to see the slide at the end of the lecture because there are interesting ways that viruses subvert this whole process. And of course, remember, the whole job of all of us is not to get your PA degree, right? It's to survive and to live long enough to procreate. That is your mission in life, right? Well, it is. And it's also the virus's mission in life. And so there is this fascinating battle between your desire to survive and procreate and the virus's desire to survive and procreate. So if it can delay your host immune response just a little bit, it might give that virus just a bit more of an edge to crank out more virus particles. And it's this interaction, this kind of arms race between 2 pretty impressive opponents, you and a virus, that I think is really, really cool. And you might sort of think, well, virus, I'm better than a virus. Actually, you're not. Think how slowly you evolve, and think how quickly a virus can evolve. A virus actually has it over you, at least evolutionarily, hand over fist, right? And we'll talk more about that as time goes on. So there is an amazing implication of what I just told you, right? An amazing implication of immune specificity is that for every bad thing that can threaten you, your immune cells can recognize it and get rid of it. That there is a T cell that is able to recognize every possible epitope that can be presented in the context of that MHC catcher's mitt. And indeed, this is true. In you right now, you have HIV-specific T cells, even if you're not HIV positive. You have Zika virus, you have Ebola virus-specific T cells that are floating around in you dormant, unactivated, nascent, but waiting for their day to become activated if, in fact, you get infected with any of those pathogens. Okay? So how does that possibly work? How is it possible that you encode specificities of T cell receptors that can recognize any of these possible pathogens? And that leads us to the second principle, which is diversity. Okay? So if you were, sorry, by the way, I apologize. I was told in one of these lectures years ago, somebody wrote a review. I've never seen my reviews, with the exception of one year. Someone wrote a review and they said, Dr. Rall was really good, but he curses too much. And I don't know that I curse a lot, but I apologize if I say something inappropriate. So this is just the preamble that as we spend another hour and a half together, God knows what will come out of me. So, so if you were God, that might be a little offensive to some. If you were God and I said, okay, design the best possible immune response, probably what you would want is to have T cells and B cells that are multi-potential, right? That can recognize lots and lots of different things, that can be multi-purpose, right? The best warrior is not the guy only who knows how to throw a grenade. The best warrior might be the soldier who is able to don't know anything about war. Throw grenades, use a bayonet, shoot a gun, drive a tractor. They can do lots and lots of things, right? But this is actually not how your host immune response works. There is the concept, unlikely but true, of one T cell, one antigen that exists. So the T cells in you that are floating around recognize a Zika virus peptide and only a Zika virus peptide. Okay? So how can you possibly encode for that kind of diversity within your own genome? There'd be no way that you could encode for all of this diversity. And this is the whole concept of VDJ recombination. Did you heard about VDJ recombination? And you don't like VDJ recombination, right? Because you're like, well, all right, but why do I have to know this stuff? Well, what VDJ recombination does is it takes this unit of DNA that is comprised of these little modules. And this is how we make a T cell receptor. So now we're not talking about epitopes. Now we're talking about how you design specific T cell receptors. And during the process of the development of those T cells, which happen in your thymus, during that process, there is a DNA splicing event. This is not like messenger RNA that splices out introns. No, this is at a DNA level in which you take a unit from each of these blocks, right? So you take one from the green block, one from the yellow block, and one from the red block. And in this particular case, a small fraction of immune cells in your body will be specific for 526 or 123 or whatever else you might end up having, right? So this seems like a lot of trouble to do, this idea of VDJ recombination, where you recombine the V and the D and the J. But the reason for this is that you have approximately 120 V genes, about 2 D genes, and about 80 J genes. Plus, did you talk about junctional diversity, where there's sort of slop as they splice these different pieces together? And you're like, really? It can't get even more complex than this. But what this leads to then is about 10 to the 18 possible different TCR combinations. And it's really smart because it allows for maximal diversity of T cells with minimal genetic cost. There's no possible way that your genome could encode for 10 to the 18 possible different TCRs. But by using this strategy where you take a little bit from here, a little bit from here, a little bit from here, splice it together in kind of a sloppy way and call that a T cell receptor, allows you to have a remarkable amount of diversity with within a fairly restricted genetic module, right? That's it. That's all we're going to talk about VDJ recombination with. So what are some of the implications of VDJ recombination? Well, there are tons of immune cells that will ultimately have no reason for existing, right? So pity the poor Ebola virus specific T cell in you, because it's unlikely you will get Ebola virus. And so every day, that T cell is like, is it my turn? Is it my turn? Is it my turn? And no, it's never its turn. And therefore, it will live and die unactivated, neglected, never used, okay? And because the process is random, because those ways in which you take V's and D's and J's and put them together, plus the slop is all random, even if you have an identical twin, your immune repertoire, that is the diversity of T cell receptors that you display, are going to be very different from your twin. And this is the reason why everyone has subtly different responses to various pathogens. Maybe you always get sick, but your sister never gets sick. It's not because you have some immunodeficiency or she has some superpower. It may simply be subtle differences in the repertoire, that is the diversity of the T cells and the B cells that she encodes that's distinct from you, and the poor luck that you might have in terms of the pathogens that you get and whether you have robust T cells that can recognize those. Okay? So positive and negative selection, another thing you don't like very much. So how are T cell receptors quality controlled once they're made? So in the thymus, you are making, imagine like this little assembly line where you're making, you say it's 1D, 1D, 1V, 1D, 1J. We'll put them together, on it goes. So there could be real risks in sending out poorly constructed T cells. With poorly constructed T cell receptors. So this is the process of quality control, positive selection and negative selection. All of this happens in the thymus, not your thyroid, that's the gland on the outside. The thymus is actually underneath your sternum, right about here. The idea of positive selection is to eliminate T cells that can't see self-MHC whatsoever, right? The ones that have no idea where the furniture is in the apartment whatsoever. Okay? The idea of negative selection is to eliminate T cells that bind to self-MHC without peptide. That is, the ones that are too aggressive. in binding. The ones that on their midnight walk to the refrigerator curse even if the furniture hasn't been moved around, right? We want to get rid, they might be amusing, but we want to get rid of them as well, right? And all of this process of quality control to make sure that the T cells that end up in the periphery, that is the ones that are surveilling you right now, are able to recognize self-MHC, but only when it's bound to a particular foreign peptide. Right? And it's always been described, I'm not nuts about it, but it's always been described as the Goldilocks idea, porridge too cold over here, porridge too hot over there, just right in the middle. Those are the ones that are granted permission to emigrate out of the thymus and populate you. So this is just me, and I could be really wrong about this, but I actually think this is interesting. So I have a lab, I run a lab, about 10, 15 people, and every time somebody new comes in, we do a mouse dissection. Because I actually think anatomy and physiology are really cool. So we walk our way through the mouse, and we usually go from feet to head. And when we get up into the thoracic cavity, the three organs that are in your thoracic cavity are your heart, your lungs, and your thymus, right? Think about how vulnerable you are down here. Your stomach, your kidneys, your liver, your pancreas, your spleen are all just, well, for you guys, a centimeter, for me, a few more centimeters away from danger. Look how vulnerable you are, right? But your chest is protected by the sternum, like this breastplate, plus the ribs, right? So there's actually a fair bit of armor that protects those organs. And the most protected of all, second only from the brain, which is encased in bone, is the thymus that lies right behind the sternum. If I were to find a place inside the body, not including the head, that if I were the organ that I wanted to be the safest, I'd pick right there. And it holds this privileged site because your ancestors, generations and generations ago, hundreds of, maybe tens of thousands of years ago, you died not because of cancer or because of heart disease. You died because of infections. And so your immune response right now is a bit of a luxury for you. You're happy that you have it. It's, good to have. We certainly know what happens if you have an immunodeficiency. But you're okay because you have antibiotics and you have, a warm, cozy home and all the rest. But our ancestors long ago, whose imperative it was to live and reproduce, their contention was to have to deal with pathogens. And so I would argue that the job of the immune response, its importance in human survival has declined with time. And that maybe the thymus evolutionarily is where it is because many hundreds of thousands, I don't know how long we've been on, many tens of thousands of years, I'll be safe, tens of thousands of years ago, the thymus was, the immune response was crucial for survival in the world. All right. So remember I said that the antigen-presenting machinery didn't just selectively pick virus-specific epitopes, but it's constantly presenting host epitopes too, right? Little host-derived peptides. Those are all the gray ones. So if that were to happen, if a host-derived epitope made its way into the class 1 MHC catcher's mitt and was presented on the surface, what could be a potential risk that results from that? What would that disease might look like? Yep, autoimmune disease, right? So recognizing a host peptide aggressively could lead to autoimmunity, right? So the T cells that survive the thymic environment are by definition, technically, only the ones that are able to recognize altered self, that is the self-MHC plus some foreign peptide. But the implication then is that during that positive and negative selection process that occurs in the thymus, that all self-antigens that you might ever express must be present in the developing thymus to exclude those autoreactive T cells. Does that make sense? We have to get rid of those autoreactive cells, the porridge too hot T cells. We've got to get rid of those because otherwise there's a real risk of autoimmunity. And for actually a long time, immunologists believed that that was right. They sort of endowed the thymus with this remarkable capacity that it could present all possible host-derived epitopes, and that the process of getting rid of self-reactive T cells only occurred within the thymus. And only about, I'd say, 25 years ago, did people realize that's not true at all. You are bubbling over with autoreactive T cells. You're filled with autoreactive T cells. And you might be thinking, well, isn't that's like 1 foot on the banana peel for getting an autoimmune disease, and that is actually sort of true. But the reason why most people don't develop autoimmune diseases is because of something called peripheral tolerance. That is, that to turn on that naive T cell, to wake it up and say, it's your turn to become an activated T cell, requires antigen and MHC plus something called co-stimulation. And that kind of co-stimulation, what I refer to here as autoimmunity insurance, is something that only can be done by professional antigen-presenting cells. Right? So you've heard about professional antigen-presenting cells, things like dendritic cells, macrophages. This is familiar. Certainly I don't want to introduce concepts that are new to you and confuse you. We're good? Everybody's hanging in there? So professional antigen-presenting cells have MHC molecules, but they also have these co-stimulatory molecules. It's almost like a second switch, right? In order for somebody to activate, this feels a little inappropriate to talk about nuclear weapons today, but in order to activate a nuclear weapon, you need to have 2 individuals hit the button. You need to have 2 go switches, right? Because otherwise, potentially just randomly triggering through one might induce autoimmunity. So professional antigen-presenting cells have 2 things. They have the MHC molecule, plus they have these co-stimulatory molecules with names like B7-1 and B7-2. So that a naive T cell, here in yellow, when it's able to recognize its respective epitope in that groove, when in the context of a co-stimulatory molecule, that will activate that T cell. Once activated, that T cell now can divide and divide and divide and find its generic target cell and go ahead and kill it. But if that yellow cell meets the generic target cell in the absence of co-stimulation, that T cell is not activated. Actually, it's turned off, actively suppressed and turned off through a process called anergy. Okay? So you actually have multiple levels of safeguarding in you to make certain that the T cells, and this is also partially true for B cells that produce antibodies, that those T cells are not going to cause you harm. The third big issue for the immune response, and we'll do this a little bit more quickly, is speed. So you have approximately 10 to the 10 immune cells floating around in you now. The average frequency of any specific immune cell is about 1 in a million. And following infection, that frequency can go from 1 in a million to perhaps 1 in 500. It requires a vast activation of, not just activation, but induction of proliferation of these immune cells, right? So you can think about this like a race. If the infection is the red line, the moment that the flu gets into you, now that virus is going to begin to do its job. Right? It's going to begin to replicate. And because, and bacteria go 1 to 2 to 4 to 8 to 16 to 32, but viruses actually, an infection of a single cell by a virus might actually result in hundreds of thousands of viral particles produced by that cell. So it's on a log scale that the infection is taking off. Remember, we talked about the idea that the adaptive immune response may take days to become activated. So there's this latency period here where that virus is replicating fairly unchecked. And it's that, let's see, sorry. It's this interval between the pathogen entering you and the activation of the immune response that's the window of opportunity for disease. Right? So how big that little triangle right here, how big that triangle is the opportunity for that pathogen to make you sick. And so it depends on lots of things. It depends upon how quickly that virus or that bacteria spreads in you. It depends on how many precursor, that is naive T cells you've got, how quickly those immune cells recognize that you're infected. So how do you maximize interaction? Well, you maximize interaction through lymph nodes. So lymph nodes are present all throughout you, right? They're actually, when they swell up, it's actually a sign that your immune response has become activated because it's all happening in the lymph node. And even though this may not be relevant so much to you guys here in Delaware, it will, I think, resonate with people in Glenside. So this is the SEPTA map for Philadelphia. If you just were to find a friend somewhere and they said, just meet me in Philadelphia, the chances that you would actually find them are pretty slim. So you end up actually having nodes, places where people can congregate or can gather. Say, meet me at 30th Street Station or meet me at Jefferson Station, right? And lymph nodes serve that same function. So lymph nodes that are present all throughout you are actually fed by 2 different circuits. They're fed certainly by the circulatory system on the right, where all immune cells naive immune cells as well as activated circulate through lymph nodes. Always are stopping by 30th Street Station just to check in and make sure nothing else is going on. But the other circuit or the other circulation that feeds the lymph nodes is the lymphatic system. So remember, we talked about that all of your surfaces are coated with immune cells that recognize foreign peptides or that recognize when you've become infected. And actually, fascinatingly, some of those professional antigen presenting cells that lie on surfaces, in your skin, for example, or in your respiratory tract, once they recognize their antigen, not only do they become activated, but they migrate. And they migrate through the lymphatic system into lymph nodes. And it's here in the lymph node that the professional antigen presenting cell meets the naive target cell, that education occurs, and that activation and proliferation begin. Then from there, those activated T cells now emigrate to wherever the infection is and fight the disease. Did I miss something here? Right. It's why swollen nodes are useful diagnostically, right? So when you have a respiratory tract infection, very often lymph nodes underneath your arms or in your neck will swell, right? If you've got a GU concern, your lymph nodes down by your groin will swell. So swelling of lymph nodes is just a measure of activation of lymphocytes within those tissues. I'm not going to actually spend too much time on this, but this kind of underscores the whole principle that if you get infected at your skin, so in epithelial cells on your skin, replication and local spread of the infection occur here, but at the same time, immature dendritic cells become mature, they migrate to the lymph nodes, and just as I mentioned, this is where they also meet T cells and B cells from the circulatory system. There is a fascinating story that may not be so relevant to you guys as PAs, but is so creepy and true that it's worth telling you. So HIV, what cell population does HIV want to replicate in? Yes, T cells. What kind of T cells? Do you know? CD4 positive helper cells, right? Where is like the best possible place to find CD4 positive T cells? Lymph nodes, full of them. But HIV, when it infects you, isn't infecting you right adjacent to a lymph node, right? Oh, somebody's calling me. That's charming. So what HIV does is it binds to the outside of a dendritic cell, binds to a protein called DC sign, and it tricks that dendritic cell into thinking that it's become activated. It doesn't actually infect those cells. It just binds to it like a fairy. But by tricking the antigen presenting cell, the antigen presenting cell wakes up, says, I've been infected with something, my job is to go to the lymph node and inform the host immune response. And in doing so, it ferries HIV directly to where it wants to go, the lymph node where sit hundreds of thousands of CD4 positive T cells, right? It's really creepy that it does this. But HIV has evolved to be able to trick your body's immune response and use this process that normally is helpful, use that process to subvert and gain access to the cell population that it wants to grow inside the most. Okay? Memory. So why don't you get sick the second time you encounter a pathogen? How many times have you been infected with chickenpox? Once? Raise your hand if you have any of you been infected with chickenpox as kids? Oh, did you not get the vaccine? Maybe not. Maybe too old.
I'm
Okay.
too old.
What, too old? Yeah. And so for those of you that have had chickenpox, how many times have you been infected with chickenpox? Once. Wrong. You've gotten sick from chickenpox once. But you've been infected with chickenpox again and again and again. Every time you encounter, and maybe less so now because people aren't getting infected because the vaccine works, but every time you encounter a little kid who has chickenpox and who says, you know, hi, Aunt Kayla, and coughs on you, you get infected with chickenpox. But you might not get sick the second time because you have memory. Right? The whole guide of immune memory, this is the principle of vaccination. And immune cells have three different lives. There's the naive, there's the activated, which we've talked about, and then some proportion, once that infection is cleared, transition into this wise old man on the hill kind of a thing where they become memory cells. And it's not dissimilar to your car in the wintertime. Car off, car running, car idling. you can mobilize to get to class much quicker if your car is warmed up and idling than if you have to start it from zero, especially if it's super cold outside. So your memory immune response is at a sort of moment's notice to become activated and respond. And this then, of course, shortens the duration or that interval that you can become sick. So in the first encounter, it takes a while for you to induce an immune response, and this allows viral loads to accumulate. In the second occasion, your immune response kicks in immediately and therefore squishes down how quickly that pathogen can replicate in you, and therefore you don't get sick, or you don't get as sick the second time that you've encountered that same pathogen. Right? You were vaccinated for most pathogens that we have vaccines for when you were kids. Right? Last time I got a measles, so I work with measles. Last time I got a measles vaccine was probably, so I'm 53, was probably when I was about 18 or so. So I have anti-measles virus immune cells floating around in me for 40 years. So how is this possible? How is memory maintained for such a long time? And there's this actually kind of cool story that I teach usually. I actually have students read the original article, which I won't do to you guys. But it's an interesting natural history tale, so I'll tell you the story. So near Iceland, in the great North Atlantic Ocean, there are this small little cluster of islands called the Faroe Islands. And prior to 1700, the residents of the Faroe Islands who had never left the islands, there was no evidence of measles virus present on the islands whatsoever. But because this was in between Europe and the Americas, sailors were using the Faroe Islands as a stopping point along their trek across the Atlantic. And so somewhere around 1700, sailors brought measles virus and probably a variety of other nasty things to the poor residents of the Faroe Islands. And in fact, because none of them had immunity to measles virus, about 90% of the population of these islands got sick with measles virus all at the same time. In 1701, for reasons that are unclear, the shipping lanes changed and the Faroe Islands were no longer used as a stopping point. And so for the next 80 years, measles virus didn't appear on those islands again. Until 1780, when the shipping lanes changed once again, the islands became a port again, the sailors brought measles virus again, and it turned out that everyone that was now quite old but infected 70, 80 years before were still protected. And it's a perfect natural history experiment because there was, remember that 10% that didn't get infected? Now those individuals that didn't have immunity became infected, whereas the 90% that were infected once before didn't. So how is memory maintained for this long period of time? And there have been a lot of debates about how antigenic memory is maintained. There were some people, this guy who actually won a Nobel Prize, but not for this idea, who believed that virus antigens or pathogenic antigens in some form persist in you to constantly re-stimulate the immune response, almost as if everything you've ever been infected with, you have a little library somewhere in your body that reminds your immune response every once in a while, hey, remember when you were 7, you had that stomach virus. Here you go. Reactivate those immune cells. That was his idea. There's somebody else, a guy named Rafi Ahmed, who believed that memory cells were long-lived, 80 years, 100 years, the lifespan of a human, which we now know isn't true. And then there was the idea of constant re-stimulation of previous responses. And this is important because if you said to me, why do I need to know this as a PA? I can't answer that question. But if you said, why is this something that is perhaps globally important for understanding how humans respond to sicknesses, I think I can explain that. Because we tried to teach you about specificity and diversity. We spend a lot of time focusing on that. But there is inherent messiness within the immune response that actually benefits you. So that's this example here, and you're a couple minutes away from a break. So if this is your host immune response and the repertoire that we've talked about, you've got some cells in you that recognize the anti-red virus, some cells that recognize the green virus. When you're infected with the red virus, you make many, many more immune cells, most of which recognize the red virus. So this is during the period of time that you're sick. And after you resolve the infection, this is what it looks like now. So you have a sort of consolidation of those immune cells. Lymph nodes now are no longer swollen. They shrink back up. And you now preserve some memory cells. Those are the car idling red cells. Okay? So now what's important is what happens when you're infected with a different, completely different virus, the green virus. Well, you make lots and lots of green cells, but look what happens to the red cells. You actually re-stimulate or you boost those immune cells as well. because the cytokines that are responsible for reactivating or for activating immune cells, turns out that they also kind of goose or spike the existing memory cells that you have in you to replicate or proliferate just a little bit, so that every time you make an immune response, you're in a way reminding your body of all the things you once had been infected with. It's kind of cool, right? That's actually, in part, how we think now immune memory functions. Yeah, let's skip over that. This is, I hope, helpful for you, and I will make sure you get, I think this is in your slide deck. I'm not going to spend time doing this, but this is my effort in the text of how to try and put all of this stuff together in terms of timing, right? So all the possible antigens you can be exposed to, viruses, bacteria, parasites, when they infect a vertebrate body, in this case a mouse, and we're using a mouse because this is in the organism in which most of these studies were done, but of course you could substitute a human here as well. Once that happens, you activate CD4 positive T cells. The job of CD4 positive T cells is to produce cytokines, which we're not going to talk much more about. And those cytokines, depending upon the flavors of cytokines that are produced, will either stimulate something called a cell-mediated response, an activation of cytotoxic T lymphocytes that will kill infected cells. That's useful if you have a tumor. That's useful if you have a virus infection that grows inside of cells. Or cytokines produced by CD4 positive T cells will activate B cells and turn B cells into plasma cells, as one of you pointed out, that produce antibodies. And these antibodies are really helpful for recognizing extracellular pathogens, like most bacteria, virtually all parasites, and other extracellular foreign proteins, other potential antigens. Okay? The kind of cytokines. So in that sense, the CD4 positive T cells are kind of the master orchestrators of the host immune response. They're the conductor, because depending upon the cytokines that those CD4 positive T cells produce, following education with a professional antigen presenting cell will dictate the flavor of the host immune response that you make, which direction you will end up going. And we'll talk about that in the second half a little bit, about how you can get sick as a consequence of immune dysfunction. The final thing, and then we'll stop, is self-control. So the immune response is nasty. The reason why you feel shitty after you've gotten infected with something, the fever, the body aches, don't blame the flu, blame yourself. It's the cytokines that you produce that make you feel poorly, right? Cells get killed, fever-inducing proteins are produced, lymph nodes get swollen, and so a very underappreciated side of immunology that's only been appreciated within, I'd say, the last maybe 10 years or so, is how does the immune response know to turn off? We've spent all of these years trying to figure out how does it turn on, VDJ recombination, positive and negative selection, thymic and B cell biology, but once you now have all of these cells that are cranking out lots and lots of cytokines and you feel horrible, yes, you're getting rid of the infection, but how does it stop? So it's imperative that the immune response knows when the job is done and turns off. And this concept of self-control is a huge issue, again, clinically, right? So it can occur by multiple mechanisms, and a interaction between two proteins called PD-1 and PD-L1 might be something you've heard about, because again, this is useful for immunotherapy for cancer patients. So the life of an activated T cell is exciting but brief, right? So that Ebola virus specific T cell in you that's waiting for its day, now sadly, if you get Ebola virus and it's that T cell's day, it becomes activated, but there's a clock that starts ticking. And within a certain period of time, through something called activation-induced cell death, that T cell will pop, will in a sense die. And this death of those T cells is regulated by expression of a variety of molecules, including things like Fas and Fas ligand, that help to turn off the host immune response. This is helpful for things like a flu virus, where you end up having a very sort of brief period of time where you have an acute infection. But for things that are longer lasting, chronic viral diseases or cancers, turning off the immune response is exactly what you don't want to do, right? Because turning off, you want that immune response to continue to be able to recognize your lung cancer, your pancreatic cancer. And so now in the clinic, there are all sorts of blockers that prevent this from happening. that prevent T cells from getting turned off that hopefully will sustain an activated immune response to be able to get rid of long-term chronic kinds of challenges, including some chronic infections, as well as cancer. Right. And these are called T regulatory cells. There's all sorts of details about them, but I'm getting tired. No doubt you're getting tired. You need a break for a few minutes. But this information's up here because they're important, and I suspect at some point clinically you're going to encounter them. So we're done with part 1. It's 11 o'clock, so we're going to give you guys a 5-minute break. 5 hallmarks of immunity: specificity, diversity, speed, memory, self-control. When you come back, so come back in just like 5 minutes, we're going to talk about what happens when the immune response works against you. What happens when things fail, okay? And I'll be up here if you've got questions for the first half. See you in 5 minutes.
And then I would have 4 drinks after lunch.
Hey, how you doing today?
Doing muscles.
A what?
I don't want what I had for lunch.
Here we go. Okay. All right. Well, most of you came back. That shows poor judgment. All right. Okay. So, good. I hope this is helpful. At the end of this, so do me a favor, and this is true for you guys in Glenside as well. Like, my email is on the end of this thing. If this isn't helpful, because like I say, you see me once and you'll not see me again. So I want this to be useful, and it's weird that it comes at the end. I don't want to, I said to a group over there, I don't want to like confuse you, especially pre-test. I'm hoping that this unites things or makes some sense of things, but if there's ways in which this can be better other than changing when this lecture comes, which I have no influence over, send me an email because I'm happy to be responsive to that. And about this, I don't particularly have an ego, so you can say, wow, that sucked and confused me and I hated it because I thought I knew something, now I don't know anything. You can yell at me. That's okay. I won't cry. So we've spent the whole first part of this talking about how cool the immune response is, how powerful, how specific, how diverse. But actually, the immune response can be your enemy in a couple of ways. And I'm just going to point out a couple of examples of how that's true. The immune response can result in immunopathology. So an overly aggressive immune response can actually cause you harm in addition to its effort to try and get rid of a pathogen. So at Fox Chase, actually, a little log rolling for the Cancer Center, the guy that hired me won a Nobel Prize in discovering hepatitis B virus and also developing the vaccine for hepatitis B. It's the very first thing that happened after you were delivered. You were whisked away from your mother and you were given a Hep B vaccine because actually one of the chief ways in which you get it is through blood transfer, which is what happens especially if you had a vaginal delivery. Hepatitis B, hepatitis C are very different pathogens. They're completely different viruses. So if you looked at how they replicate, which we won't, they're remarkably different, but they cause the same disease. The diseases that they cause are liver cirrhosis, which is like a scarring, fibrous tissue within the liver, and in many cases, liver cancer. Right? So second only to alcoholism, this is the chief way in which people get liver cancer. And it's not because of the virus replication, it's because of the host immune response. This is a chronic, long-term infection. The immune response is constantly trying to fight it. And in doing so, there is a lot of cell damage and cell death that occurs. And this is all attributable to immunopathology, not to the virus itself. Another way that isn't a virus-specific way or a pathogen-specific way in which the immune response can be bad is in the case of tissue grafts, right? Particularly for your patients that are going to be receiving bone marrow transplants. And this is my only gross picture to show you, but graft versus host disease. So remember, we talked about your immune response. Put up some of your names, because I'm going to start using your names, which will embarrass you. You'll hate it. So Jessica, I'm sorry. So we talked about that Jessica's immune response, that her MHCs know who Jessica is. And that if Jessica gets infected with influenza or with the common cold, that her T cells are going to be able to recognize that because it's not Jessica. But if we were to transfer immune cells from Kayla into Jessica, Kayla's cells are going to be perceived as foreign, just as if Kayla's cells were, influenza virus. It's not a matter that it's an infectious agent. It just matters that it is not Jessica. Does that make sense? So if we transfer in, this is the whole reason why blood typing makes a difference, right? We can't just take any old blood and pop it into a patient that needs it, because that patient's immune response will rebel against the transferred in blood. Or conversely, if the transplant contains immune cells, you could end up getting graft versus host disease. The immune cells within the graft, which doesn't necessarily just mean a skin graft, but could also be a blood donation or a bone marrow transplant, could respond against the patient. All of this is ways that your immune response is doing what it thinks is best for you, right? Jessica's immune cells are going to be like, I see something foreign, but that foreign thing are Kayla's immune cells trying to make Jessica better, but in fact, the immune response doesn't know good from bad, it just knows me from not me. Graft versus host, pretty awful thing. We actually see it fairly frequently at the cancer center because patients are recipients of bone marrow transplants where this is often is a side effect. On the flip side of an overly aggressive immune response is immunosuppression, when your immune response doesn't work particularly effectively. So what's a virus that causes immunosuppression? What's the big virus that causes immunosuppression?
HIV.
Wonderful, thank you. Right, and HIV, HIV causes immunosuppression through a permanent loss of CD4 positive T cells. Remember, we talked about them being the conductors of the orchestra. If you take them out and you just have an orchestra now with no music and you say, play something, it's going to be not nice to listen to. There's going to be a lack of control and coordination among the orchestra if you don't have an effective conductor. And likewise, patients with HIV, you don't actually die of HIV, you die of all of the infections that you get because you're immunosuppressed, because you don't have CD4 positive T cells. So infections like pneumocystis, a lung infection that a lot of people can, with intact immune responses, can fight, patients with HIV can't because they don't have the coordination to be able to do so, right? And HIV is still a huge, huge issue, right? So since 1981, over 30 million people have died. Currently, there are a greater number of people living with HIV than have died of HIV. That's terrifying to know, right? And even though there are drugs that are out there that are helpful in combating or prolonging HIV, and indeed, an achievement of which I think we all can be proud is that HIV has gone from a fatal disease to a chronic disease. Nevertheless, it is a chronic disease. And these patients still suffer ramifications from this. There's a huge difference in the world population of where patients are infected. And I apologize if I seem a little political in this. Very often, Africa is referred to almost as whenever we talk about where pathogens replicate and spread, Africa tends to be a hotbed for this. But I want to kind of point out that Swaziland is in Africa, and indeed, a quarter of the population of Swaziland in Africa is HIV positive. But guess what? So is Ethiopia, in which a population is about 1.4%, somewhere around just a little bit higher than the United States. So it's a personal pet peeve when people talk about Africa as if it's one country and that everything is kind of the same and that there's pathogens that rage, because indeed, Ebola virus, Zika virus, a lot of them originate from countries within Africa, but it's a little political point. There's a second virus that actually causes immunosuppression, and so take off your PA hat for a minute because you don't need to know this, but it's actually sort of cool, and so I'm going to tell you about it because at the end of this, I want you just to get a sense of, wow, viruses are creepy and creative in how they can evade host immune responses, and it's the virus I work with. I do not mean in any way to equate measles virus immunosuppression with the severity of HIV immunosuppression, not at all, okay? HIV, much more important. But measles virus is at least scientifically a little bit more interesting. So remember we talked right at the very end when you were wishing that you were going to get a break. Remember we talked about different profiles of cytokines, Th1-like cytokines and Th2. Did you talk about this? in your class, like Th1 cytokines that are responsible for recognizing infected cells. So cytokines like interferon gamma, IL-2, and then there are, and so these are particularly good when an antigen-presenting cell can trigger a CD4 positive T cell to make Th1-like cytokines. That favors getting rid of infected cells. And conversely, antigen-presenting cells that can stimulate T cells to produce Th2-like cytokines like IL-4, IL-5, IL-10, those cytokines are helpful for turning on antibodies and for getting rid of extracellular pathogens. Remember we talked about this a little bit? Okay, so how does a CD4 positive T cell know which battery of cytokines to make? Well, that's actually dictated by the antigen presenting cell and one particular cytokine. It's the only one that I'm going to kind of talk about in just a little bit of detail by name, called IL-12. So when IL-12 is produced by a professional antigen presenting cell, it skews the T cell to produce Th1-like cytokines. And those Th1-like cytokines are helpful for virus infections. IL-12 leads to that. So how does measles cause immunosuppression? This is really cool. Measles virus that can replicate inside antigen-presenting cells turns off IL-12. So you actually do make an immune response when you're infected with measles virus, but you make the wrong immune response. You make a Th2 response because there's no IL-12. So now you're producing IL-4, IL-5, IL-10, perfectly good cytokines if you have a bacterial infection, absolutely useless if you have a viral infection, right? So that's insidious. That's pretty clever. That this is a way by which a little virus, and measles virus encodes 8 proteins, that's it, 8. This little virus that encodes 8 proteins, most of which are structural proteins, can somehow trick the antigen-presenting cell to not make a cytokine that completely skews the immune response to the wrong direction. Now, eventually, your immune response catches up. You get rid of measles virus, and after you've resolved that, your immunosuppression is, you are no longer immunosuppressed. So unlike HIV that's permanent, measles virus immunosuppression is just transient. But if you're a kid in a developing country where you're drinking perhaps unclean or unpurified water, or week-old green curry or something like that, then just for you, then there is a real risk that during that period of transient immunosuppression, you're going to become very, very sick. And indeed, that is the basis of a lot of the deaths that measles virus causes. There's another way too. We'll skip over that. Bigger viruses, like DNA viruses that encode 20 to 100 proteins, have even more creative ways of doing this. We're not going to spend time on this, but this black and white part of the slide you saw before. This is antigen presentation. And what I've done is overlay on top of this in different colors, different viral proteins that somehow stop the process of antigen presentation, right? So I'll just refer to one. Adenoviruses that cause sort of common cold-like symptoms encode a protein that tether the class 1 MHC molecule inside the ER. So even once one of these epitopes makes its way to the ER, and that little trimolecular complex that we talked about is formed, this viral protein holds back the MHC molecule, preventing it from going to the cell surface. By doing that, it delays the ability of the host response to recognize that this pathogen exists, and it buys that virus just a little bit more time, maybe just an hour, in order to replicate, fulfilling its mandate to make more of itself, right? Fairly clever that these viruses have evolved these very precise tools to prevent your host immune response from working at peak capacity. And I think things like this are interesting because viruses don't have brains. They didn't sit down and draw out the antigen presenting scheme. But viruses can evolve quickly. And so little mutations that allow for these proteins to emerge are rapidly selected for because it gives those viruses a replication advantage. And that's what you're facing, these rapidly evolving pathogens that can be quite scary. Despite your intelligence as a human, you don't evolve very fast relative to them. There are even more boutique ways that the immune response can cause damage. So we talked about these epitopes as being the primary thing that MHC molecules present. It's also true for B cells. Their B cell epitopes are different in the sense that they're not presented by an MHC molecule, but nevertheless, it's a portion of a pathogenic protein that's being recognized by antibodies, just like it's an epitope that's being recognized by T cells. But that's 7 to 9 amino acids. What if that little piece of some scary viral protein, just by chance, looks like a little piece of a perfectly normal cellular protein? A cellular protein that is very different, the rest of it, but that epitope looks the same. Well, now it's possible that an antiviral T cell or B cell activated to this, it's not going to be able to distinguish between whether that's a foreign protein or a foreign entity that's encoding that protein, or you that's encoding that protein. Does that make sense? And if we've gotten past the antigen, the professional antigen presenting cell co-stimulation event so that we've activated these things successfully, now you might end up getting antiviral T cells that by pure mistake are recognizing and now killing your host cells that might not have that infection whatsoever. It's a different way to cause autoimmunity. And it is not clear whether human diseases whether there are specific human diseases that follow this. There is the suggestion that there is an eye disease called stromal keratitis that is induced following herpes virus infections, for which this may be true. But I suspect that there are going to be more and more cases of this idea of molecular mimicry, where the same epitope is presented, in one case an epitope from a virus or a pathogen, in another case an epitope from a host that can trigger untoward effects. Okay? And even in the context of tumors, immune cells you would think would be useful making an effort to try and get rid of that tumor cell, but actually a lot of the cytokines that immune cells produce, and I just highlighted this right here in the middle where it says release of growth, survival, or angiogenic, that is blood vessel promoting factors. Immune cells produce all these things too. And so even though an immune response that migrates to a nascent, let's say, lung cancer is trying to do you good, is trying to get rid of that lung cancer, the molecules that it produces might actually be pro-tumorigenic, might enhance tumor survival, tumor cell division, or tumor survival. So, okay, last bit, vaccines, a little bit of nuts and bolts, and then I promise I'm going to save 15 minutes, 20 minutes for the sociological issues. Okay, we're good? What's the most devastating disease in all of human history?
Smallpox.
Yep, good. Smallpox. So smallpox looks like this. It has killed over 300 million people in the 20th century alone. This is more than twice the number of deaths in all world wars. It killed greater than 100 kings, queens, monarchs, including Ramses, and even Pocahontas. And I had a slide of Pocahontas from the Disney movie with little red dots all over her face, but I felt like that was too dark, so I took it out of it. But smallpox made a huge difference. But you don't have to worry about it. You will not likely ever see it in your clinic unless it is the end of days, because this is a virus that has been eradicated. Yay, humans, for getting rid of this. And it got eradicated because of a successful vaccine. This is extra credit. I don't think you'll know this. What's the only other virus that has been eradicated? If you know it, I will be very impressed and proud. It is a virus that doesn't infect humans, actually. It's a virus called Rinderpest virus. And Rinderpest infects cloven-hooved animals like cows. It actually matters because it was a huge agricultural problem. It's a relative of measles virus, and we were able to eradicate it as well. There are other viruses like polio and measles virus that are on the short list for eradication, but as we'll talk about in the waning minutes, it's unlikely to happen, at least in my lifetime. Maybe it'll happen in your lifetime as well. But fully eradicating a virus, especially one like smallpox that causes the kind of devastation that it has caused, is no small feat. You know, and you don't think about smallpox. It's not in your orbit to worry about. But this was a remarkable accomplishment. Poliovirus, these viruses have been around forever. So 1400 BC, there is this it's called a stele, S-T-E-L-E. It's like an engraving of a Egyptian prince. And if you look carefully at it, you see he has a withered leg. So this is actually taken as general evidence that this guy actually had poliovirus. He also is carrying a staff that helps to support him. So poliovirus has been around for thousands of years, has impacted human populations, and even as recently as 1953, caused people to be, so this is a infirmary in I think it's a school gymnasium, of people that were sequestered. What's that word? Quarantined, thank you. Quarantined who were poliovirus positive. So viruses have made a huge difference, and therefore vaccines against them are remarkably impactful. Do you know what happened in 1793? What major epidemic happened in 1793? Nope. Happened, I'll give you a hint, happened near here. It happened, that's Philadelphia. Do you guys ever go to Philly? Philly's a cool city. And it happened right here along the wharf. Does that give you a clue what the pathogen was? 1793? No? Yellow fever. So in 1793, there was a yellow fever epidemic. And this is called Helltown, which now is right around Market Street. The Continental Martini Bar is located right here. I would recommend it to anyone. But this is fascinating. This is actually a map that documents proportion of patients or of individuals that died. 20 to 67% of the population on that street died of yellow fever. This was at a period of time right after 1776. This was the nation's capital. George Washington was here. And all of a sudden, humans had no idea what viruses were at this time, and all of a sudden, people just start dropping dead. Whole families obliterated. People, young children, older folks as well, and they actually began dying in this kind of pattern. And if you look at this, it almost looks like a bullseye, right? The redder the color, the higher proportion of patients that died. So if you had to take a reasonable guess as to where the incipience, the beginning of that epidemic occurred, you probably would point to somewhere right along the right along the wharf there by the Delaware River, right by the H in Helltown. And you'd be correct. Because, so as I mentioned, in just 10 days, this actually happened in August of 1793, 1 in 10 of all Philadelphia residents, about 50,000 people, died of this mysterious illness. 1 in 10, right? Imagine, I mean, I don't mean to be graphic about this. Imagine if all of a sudden 1 in 10 of you all of a sudden just disappeared. The 9 of you that remained would be freaking out. And indeed, in Philadelphia, they were. No one knew what viruses were. And people actually thought that there was something poisonous in the air. And so they were exploding cannons. This seems like crazy behavior, but they were actually exploding cannons to purify the air because they felt so terrified by what was going on. Benjamin Rush, who's actually considered to be one of the fathers of American medicine, proposed incorrectly that rotting coffee beans by the docks were the cause of yellow fever. He was right that it was something by the docks, but it wasn't rotting coffee beans. Washington and his cabinet fled. Benjamin Rush suggested incorrectly that African Americans were somehow naturally protected from yellow fever. African Americans stayed behind, were caregivers to a lot of individuals, but of course they were not protected. They died too. And the cause of this were mosquitoes. So right along the wharfs, there were little collections of fresh water. Those are great breeding grounds for mosquitoes. And indeed, so mosquitoes, here we go. It took forever to animate, so enjoy this. There we go, mosquitoes. Mosquitoes were the cause because mosquitoes delivered yellow fever. And they're little flying syringes, right? In order to get past that, remember what we talked about, the holistic barriers that you have. Your tough, dead outer surface layer of skin provides a nice protection against everything else. Unless you've got a flying syringe that is able to somehow poke its little proboscis beyond those dead skin cell layers and inject the blood that contains the yellow fever virus directly into your bloodstream. Right? So mosquitoes that also carry West Nile virus, that also carry Zika virus, are kind of terrifying, right? There are good things about this too. It actually led to the world's first city sanitation program. In fact, Philadelphia, you may not know, was a world leader in developing sanitation programs. You wouldn't know it today, but it turns out that this is also true. Viruses can spread super quickly. I want to kind of go a little quickly through this because I want to save time for the autism thing, but this is just how quickly West Nile virus can spread. In 1999, it actually began with 5 individuals in Queens. And by just 5 years later, 4 or 5 years later, this is how widespread West Nile virus was. Do you know how West Nile virus began in the United States? It is presumed, nobody knows this for a fact, a single mosquito. A single mosquito that was an invisible passenger in probably someone's luggage who was traveling from Israel to New York. That mosquito, once in New York, came out, bit somebody, and that is actually what began this whole cycle. How do we know that? Because the virus that we can sequence from those 5 individuals in Queens traces back exactly genetically to a West Nile virus isolate that can be found specifically in geese in Israel. So it's presumed that there was some sort of vector, probably a mosquito, that made its way across the pond to Queens. Kind of curious. Okay, so PAs, which of these viruses should mankind be the most worried about? You get to pick one. Anybody want to be brave and shout it out? Flu. Right, so not to be dismissive, but it's not HIV. HIV is actually nasty if you get it, but it's very hard to get. Okay, and it's not something that we tell high school students, probably, but it is actually very difficult to get because the virus actually has to get into the blood, right? So this is the reason why gay men actually are at such risk, because gay men have anal intercourse. Anal intercourse actually promotes the juxtaposition of contaminated or HIV-positive semen with broken blood vessels. Right? This is actually why it's a bit challenging for heterosexual intercourse to result in it. Doesn't mean it doesn't, but it's more difficult for that to happen. This is the reason. And actually, I think there's a fair number of people that don't quite know why this is such a prevalent disease within the gay male population. So hard to get, therefore, it's not unimportant, but it's not likely to be a huge epidemic. Zika virus is not something that most of us as virologists are particularly concerned about. Although I got to say, as a virologist myself, I think that might right now come in second, because flu is the first one, you're right. The changes in temperature, because climate change is not a theory. The changes in temperature mean that the migration patterns or the habitats of these mosquitoes that carry these terrifying diseases also changes, right? And so as the weather gets warmer, as Philadelphia and Delaware encounter progressively warmer and warmer climates, guess what? Mosquitoes are going to want to live up here that were normally restricted to equatorial regions. And they will bring with them their nasty things like Zika virus. Zika virus is a strange virus because of the things that it can cause, like the microcephaly in kids. So it's not something to sneeze at. For sure. West Nile virus is not something that worries too many people. Even humans that are infected with West Nile virus survive it reasonably well. And it doesn't seem to have the same kinds of prenatal effects, at least that we believe, that Zika virus does. And Ebola virus is also a disease that's actually quite hard to get. It's not transmitted by aerosols. So if I was Ebola virus positive, I told you right at the beginning, if I were to sneeze or cough, those little droplets would permeate back to you. You would not get Ebola virus from me. You'd actually have to be in physical contact with my secretions, my mucus, my urine, my feces that would contain it. And that physical contact causes problems. But that's easy to prevent. You wear gloves, you wear masks, and actually there were a lot of caregivers of patients with Ebola virus in parts of Africa that survived perfectly fine through precaution. So you're right, influenza virus is the virus that we all worry most about. It's the magical combination of ease of infection plus serious illnesses, right? I could have the flu, I could cough, and I could infect all of you with that flu without moving from this spot. So this is why you want your patients to get infected. Yeah, this is why you want your no, you don't want your patients to get infected. Let me try it again. This is why you want your patients to get vaccinated. And we're going to talk about the importance of vaccines next. So how do vaccines work? I referred to the new dog on the block analogy. You're walking down your street. There is a new cute little dog. You're like, oh, a new dog. I'm going to bend over and pick this dog up. And all of a sudden, this dog does this, right? It also freaks you out because it apparently changes color. So the next time you walk down the street and you see the same little bastard, what are you going to do? You're going to walk across the street. You're not going to touch it, right? This is actually an important concept. This may seem silly to you, but your memory triggers a change in your behavior, right? It's not just, oh, I remember that dog, and you're going to lean over and, encounter this again. It's going to change how you behave. And likewise, the immune response's memory triggers a change in how your immune response deals with pathogens. That is, past experience informs your behavior. If we're able to vaccinate patients against particular pathogens, polio and measles virus shown here, the next time they encounter that real pathogen, not the vaccine, but the real pathogen, they're now going to have this lightning fast immune response because of the establishment of memory, and now they're not going to get sick, right? So you all know this, I'm sure, but vaccines are just crippled forms of the very pathogen we're trying to prevent you from getting. And we can cripple them in a variety of different ways. We can heat and activate it. We can UV it, so we sort of change its genetic structure. We can cripple it by so something called attenuation, where we passage it multiple times. So the virus grows a little bit, but it's hobbled, and therefore that period of time that it takes to accumulate is much, much slower, and therefore your immune response can get in front of it faster. There's lots of different ways in which we can recreate them, but there's undeniable success in vaccination strategies, right? So measles virus was introduced the year I was born, 1963, and we went from a reported number of about 600 million 600 patients per 100,000 in the population to fewer than about 50 within the United States in a period of, looks like about 10 years. That's remarkable. And this just lists, don't worry, it's a table. Nobody wants to look at tables. But if you just look along the left, you see rubella, smallpox, mumps, diphtheria. The only thing you have to pay attention to is the percent decrease following introduction of the vaccine, right? So I think I'm preaching to the choir, although maybe I'm not. Vaccines work. They are impactful. Your patients need to get their vaccines. This is a little bit of detail about different ways that we can make vaccines. I'm going to kind of skip over it, but simply what I said before, that you can attenuate viruses so that they are a little weaker, a little less effective, but they're still able to grow. You can inactivate them. You can fractionate them. You can use individual pieces of the virus. So instead of giving them the whole measles virus, you can just give them one particular protein that might induce an immune response. All of them have pros and cons in terms of efficacy and duration, but there's lots of different strategies that we can use. And some of the ones that are toward the right are the kind of newer age approaches that combine efficacy with lack of side effects, including subunit vaccines and virus-like particles. We're not going to spend too much time on that. If you were in a virology class, we would spend probably a full day talking about each of those things. But just know that there's a variety of different ways in which vaccines can be delivered against a variety of different pathogens, not just viruses. Okay. So why is vaccination important? So it's a community act. So now my little circles represent people, not cells. And we have two neighborhoods, neighborhood 1 and neighborhood 2. If let's say in neighborhood 1, everybody that's shaded blue is vaccinated with, let's say, the typical wild type strain, and in neighborhood 2, it's that proportion of patients. True or false, future PA students, this person is as susceptible to the infection as that person. Is that true or false?
False.
Why is it false? Herd immunity. Right. So herd immunity is the concept that the higher the proportion of people within your population that are vaccinated, the safer is the individual who is not vaccinated. Okay? So indeed, neighborhood 2 is much more permissive to infection. And you should care about this because you're not just a victim of an infection. You are an incubator. You are a vessel. And remember, these viruses mutate like crazy. Yeah? So if in one of those individuals in neighborhood 2, well, I didn't include this in here, but if in one of these individuals in neighborhood 2, a mutation were to occur that gives that virus, now let's call it a light blue rather than a dark blue virus, a little bit of an edge. Now everyone over here is permissive now as well. Okay? Because you're not vaccinated against all of measles or all of polio, you're vaccinated against the primary predominant strain in the population. If there is a mutation that causes that strain to be different, now nobody is vaccinated, right? So this idea of a community event or a community act where vaccinating yourself actually contributes to herd immunity within the human population is no joke, right? Who are we going to pick on? Michael. I'm going to pick on Michael. So if Michael's parents decided not, do you know Michael? You've only been around for like a week or so. Do you know what? Michael's parents didn't vaccinate him against measles virus. It's ridiculous. But fortunately, all the rest of you were vaccinated, and therefore you formed this immunological wall around him so that measles virus can't get into this community, and therefore he is protected not immunologically, but kind of indirectly because all of you were vaccinated. And this comes down to this importance about the autism debate that we'll get back to. So Michael, I'm not done with you. So measles virus, just a quick vaccination example. I don't care that you know anything about measles virus, but it's the thing that was accused most aggressively of its association with with autism and vaccines. So humans are the only natural host for measles virus. Communicability is extreme. It's actually the most communicable of all infections, more than the flu, more than Ebola or any other transmitted virus. It has a long infectious period, which means infected individuals are shedding virus for a period of a couple of weeks. Vaccine coverage in the United States is good. It's why you don't think it's a big deal anymore. As I said, it was introduced in 1963, and it reduced the annual rate by 98%. If my career could be to introduce a vaccine that reduced the annual rate from 4 million to fewer than 100, I'd say that's a life well lived, right? And coverage has remained pretty high, about 91%, but in some cities, coverage is only about 50%, including parts of Philadelphia, because school nurses are not as aggressive as they probably need to be to make sure kids are vaccinated before they come into class. Measles virus can cause a lot of death worldwide, but you don't know about it because you live there. That's the Pan American Health Organization. This is from 2000, so it's a while ago. But look, Africa, Southeast Asia, these numbers, you may not be able to see it because it's kind of small, but it's 400,000, 300,000, greater than 1 million people each year. Even still, hundreds of thousands of people die of measles virus, not just get infected by measles virus, die of measles virus each year, even today, even now. Most of them die because of pneumonia and lung complications or because of those diseases we talked about when kids are immunosuppressed that we mentioned earlier in this half. Let's skip past some of this stuff. But measles accounts for about 37% of vaccine-preventable infections. So what's the vaccine controversy? So in 1998, that article appeared in Lancet, with the kind of anodyne title of ileolymphoid nodular hyperplasia, nonspecific colitis, pervasive developmental disorder in children. So it doesn't say measles and it doesn't say autism. It's actually a hard article to find. And this report linked vaccination of kids with the MMR vaccine, measles, mumps, rubella, with subsequent PDD, or pervasive developmental disorder, now known more as autism spectrum disorders. So scientists do what they do best. They're like, really? We didn't think so. So let's find out if this report is right. And so there was this whole series of international retrospective and prospective studies to find out whether vaccines, particularly the MMR vaccine, is linked to autism. And that's fairly straightforward to do. We take a cohort of kids that have been vaccinated, we take a cohort of kids that have never been vaccinated, and we say, what's the autism rate in these two populations? If they're different, then maybe vaccines had something to do with it. But they weren't different, they were the same, right? And this is what study after study after study supported. And therefore, the scientific community pretty quickly said, no, this is all BS. There is no connection between vaccination and autism, right? Nevertheless, I guarantee you that if you walk out, well, you don't want to walk out on that main street, but if you were to go to the mall across the way and you were to ask any average person at Home Depot, hey, tell me what you know about autism, 9 out of 10 of them are going to somehow, in that conversation with you, use the word vaccine. I guarantee it, even today, and this happened in 1998, right? This reduction in immunization has resulted in outbreaks in the United States, in Europe, in other countries as well, and we're now seeing that curve that went down in terms of the number of kids that are infected with measles virus is now back up again. Right? And measles virus, we won't talk more about this, but it's not just a childhood rite of passage. It is not trivial. Kids get hospitalized with this. It makes a difference. And I love this. This is the only actual piece of data I think I show you, but it's really important because it talks about herd immunity. This is important to me. So this graph measures two things. On this y-axis, it's looking at the percent of MMR uptake. So it's in a sense, a measure of herd immunity, right? So these levels hover somewhere around like 93, 94%, right? The blue line is measured on the y-axis on the right, and that's the number of cases of measles virus. So this is actually from Britain. What year? So years between 96 and 2009. So look, when herd immunity drops somewhere down around 80%, look at how the change in the number of cases of measles virus, how that goes up, right? This is a natural human experiment where when herd immunity, at least for measles virus, dips below even 80%, so even if 80% of you were vaccinated, is not sufficient to provide protection for Michael from getting measles virus, because when it dips below a certain level, the number of cases of measles virus goes up. This paper that I referred to had a variety of other chilling subsequent revelations. So misconduct issues were a concern about this paper, resulting in all but one of the authors who selected to remove their names from the paper. Wakefield, a guy I know, who was the remaining author, lost his physician credentials in the United States. The paper was retracted. The Examiner in Britain called it the most damaging medical hoax of the last 100 years. I teach a class at Penn on the most impactful papers within science over the last 50 years, and I talk about this paper. And it pisses them all off, right? The Penn students are like, well, but they want papers to talk about discovery of oncogenes and things. But I would actually argue that this paper has had more of an impact on public health responses to available medical resources than any other paper, even though this paper is incorrect and actually unethical, because if you read, the funding for this came from anti-MMR campaigners. 9 of the 12 kids had essentially normal biopsy reports, even though that was ultimately changed to colitis and on and on. So this then results, this is actually just, I think, 2016. This is the number of reported measles virus cases throughout the United States. And you'll notice it's not just one here, one here, one here. It happens in groups because we all form little herd immunities in our respective communities, okay? This is 2015, and this big number here, 92, do you know what that's associated with? Where is that? I mean, California, but where? No, actually, maybe the 92 belongs a little bit lower. Did you hear about this? So Disney World. So there were kids that had measles virus that were at Disney World, along with a bunch of other kids who probably were too young to have gotten the vaccine. And this resulted in a remarkable outbreak. And actually, 92 can be traced back to this one child who was able to infect 92 other kids in Disney World on that, or Disneyland, I guess, in that one particular day. And some of those kids actually then ended up going back and continuing to transmit it to others of their colleagues who didn't go to Disney World. There is, if you're a John Oliver fan, I'm a huge John Oliver fan, watch this. This will be better than the 2 hours that you spent with me by far. Just last week, he had an article about vaccines. Did any of you see it? Yeah, there you go. I don't know how you have time to watch John Oliver, but if you do, it's funny, but it's also chillingly smart. So you will hear this story sort of retold by a much funnier guy. So why are people still so worried about the vaccine? Why does this have such prominence? Why is it a thing you might have to deal with in your clinic? Well, first of all, one thing that's true is there is an alarming escalation in the rates of kids that are diagnosed on the autism spectrum, okay? 1 in 68 kids. It has this sort of bizarre regional specificity. Alabama has the lowest rate. New Jersey has the highest rate. I believe, but I'm not sure, that Brick Township has the highest rate within New Jersey. I'm sorry. And people used to think, well, is this really a change in the total number of kids, or have we just gotten better at diagnosing it, right? Because I can't do a blood test on a kid with autism and say, oh, okay, because you have high levels of protein X, you must be autistic. It's a guide based upon non-measurable entities. Let's put it that way. So there was actually a really cool study that was done that actually used 2014 knowledge and applied that knowledge to medical records from 1970 something. And they said, if we knew in 1970 what we know now about how we diagnose autism, how many kids with those records would be diagnosed with autism back then? And it was some portion, but it didn't account for the total number of increased changes. I think a third of them might have been diagnosed with autism then that weren't diagnosed with autism. But there is a true increase in the number of kids who have autism. So we as scientists don't know the reason for the increase. So that's terrifying to parents. Maybe some of you are parents or future parents or aunts and uncles of kids that are scared about this, right? So it is terrifying why the rates of autism are increasing. So therefore, it makes a little bit of sense why people would be looking for non-genetic environmental factors that might contribute to increased rates, right? But then there's also this issue of true, and unrelated, right? So you'll enjoy this. This is not a slide you have. So top and bottom are measuring two different variables. Don't look at the left and right, just look at the lines themselves. If I were to say to you, are whatever the red line and the black line measuring in the top and the bottom, are they somehow connected to each other or not? The average human would probably say, yeah, they're pretty connected, right? When the red line goes up and the black line goes up, they both go down together, they kind of rise and fall. So let's see what the red and black line are. For the top one, red is the number of letters in the winning word of the Scripps National Spelling Bee, and black is the number of people killed by venomous spiders. And the bottom one is the age of Miss America compared to the murders by steam, hot vapors, and hot objects. Right? So it's funny, but it's actually telling. You are smart. You are a human. You are smart. You put pieces together. You look for rationale where rationale doesn't exist, right? These things are not correlated to each other, but you can be forgiven for thinking that they might be correlated with each other, especially when you look at the scales on the left and right, how the data can be manipulated to suggest this. So I think this all contributes to the idea that two things are true. Kids are getting more vaccines these days than before. That's true. And there are more kids that have autism than before. That's true. Those two things are true, but they're not related events. Right? And this is part of the challenge of you and how you communicate this with your patients. The second, or the third reason why people, I think, are worried is controversial. And feel free to fight back. Again, you're not going to see me again, so you can't upset me if you're like, this is all ridiculous, I don't like this. But I actually would argue that not vaccinating your child is a logical decision. I think it's a wrong decision, but I think it's logical. So raise your hand. And now I need all of you to help me with this. It's a little bit of a personal question, but it's okay. Raise your hand if you've ever seen a case of measles virus before. Look around. I'm sure you see. Not one. Me included. Even though I work on it, I've never seen a case of measles. Now, raise your hand if you know someone who is on the autism spectrum. Look around. Virtually all of you. So now you're going to be asking parents of your kids in your clinic to vaccinate their child against a disease that is an abstraction to them, a disease they've never seen before. And so therefore, if there's even like a scintilla of truth to the idea that vaccines might cause autism, a rational parent might be like, well, let's see, she wants me to vaccinate my kid against measles, but I don't know of anybody with measles. The chance my kid's going to get measles virus are zero because my life experience is zero. But if there's even a little bit of a potential that vaccines somehow contribute to autism, that makes me nervous. So maybe I'm going to delay. Maybe I'll wait until my child is 4 or 5 rather than 18 months or so. Okay? That's logical. It's wrong because there is no correlation between vaccines and autism, but that's logical. So don't you dare talk down to your patients. When patients come in and they say, I don't think I want to vaccinate my kid, don't get the white coat finger waggy, listen to me, you don't know what you're talking about. They're actually using a fairly logical process to come up to the decision that they're making here. Right? And it's important. This I'm going to read to you because I think it's important. Voluntary vaccination policies, I think it's fascinating. For childhood diseases present parents with a subtle challenge. If a sufficient proportion of the population is already immune, either naturally or by vaccination, then even the slightest risk associated with vaccination will outweigh the risk from infection. As a result, individual self-interest might preclude eradication of a vaccine-preventable disease. Right? So, if one of you, if Michael's parents say, I just don't know, I'm not going to vaccinate Michael because I'm a little bit concerned about that, he's going to be okay as long as the rest of you are vaccinated. But now, if Michael's parents and Catherine's parents and Megan's parents and Taylor's parents and Laura's parents all now make that same decision, herd immunity drops, and now that blue line that we talked about begins to increase, right? And now this is how viruses like measles, but not restricted, of course, to measles virus, have an opportunity to sneak into a population that otherwise could be prevented through vaccination. We're good? Almost done. If I go a few minutes long, is there like something coming in right after me, or you have can you give me 2 minutes longer? Okay. I think a fourth thing, and sorry, I'm a PhD, so it's not like I have any experience in human behavior, but I'm also older than you, so just suffer through this. Humans are complex, right? And we are motivated by many often conflicting beliefs and emotions. You may have noticed over the last 2 hours that I'm chubbier than I need to be. And indeed, physicians have said, Glenn, you may want to lay off the donuts. However, if one of you had baked fresh donuts and they were sitting right there, the chances that I'm going to eat one of those donuts, 100%. So even though my medical professionals have said, you might not want to. I'm using a complex set of decision-making processes going on up in here to make a decision that is in my poor interest health-wise, right? And likewise, and please don't laugh at this. I actually used to put this up and mock it, and now I feel like a jerk for doing that. So one of the biggest outbreaks happened in 2012 in a population of individuals that lived in Texas that were part of a large megachurch that was run by this guy, Kenneth Copeland, who is a TV minister. And one of the women in his congregation said, to get a vaccine would have been viewed by me and my friends and my peers as an act of fear, that you doubted that God would keep you safe. You doubted that God would keep you healthy. We simply didn't do it, right? So you, as a PA, are going to be one little piece of information that your patients or the parents of your patients get to hear. But you are working against their faith, their peer group, potentially peer pressure, their own cultural biases, a variety of other things. So you are just one voice in this kind of complex wilderness that's trying to have an influence about healthcare decisions that they may make, not dissimilar to the example of me and donuts, all right? So factor that in as you actually interact with these, with the parents of kids that you're trying to get vaccinated. So as scientists, and now you're part of this, right? Any of us that deal in the sciences, whether it's through clinical practice or through studying how these viruses replicate or how science works, we have a whole lot of challenges in how we communicate to our end users, because it's not just about VDJ recombination and T-cell development. Yeah, okay, good. Will you be smarter if you know those things? Yes. Will it make you a better PA? I would argue not. Communication will make you a better PA. And how you communicate things effectively in a non-pejorative, non-finger-wagging way to your patients seems like it would be fairly important. Speaking as a patient myself, I want someone to be able to respect me when they talk to me about my own healthcare, right? But there's all sorts of things that fight you. There are science-y websites and a little bit of truth and a generally science uneducated population. They know all about what's happening with the Kardashians. They don't have a clue what's happening with vaccines and autism, right? We have well-intentioned, with respect to autism, we have well-intentioned, passionate parents who believe that vaccines are indeed the cause of their child's autism. I give talks, used to give talks to lots of parent groups about this. I've met them all. They have offered to show me their child's second-year birthday party videos when I will see for myself that their child was normally functioning and then got the vaccine, and now their child has this regressive disorder, right? So they believe this passionately, and they're very vocal. There is the need of the media, who still keeps this process alive, to present both sides of an issue, because it's not a very exciting story for a TV news reporter to come on and say measles virus doesn't cause autism. It's much spicier if we get a physician who says there's no relationship, and then a mom or a dad who's got their autistic child with them to say, this child is my evidence. That's compelling. That's hard for you to fight against. It is complex. We kind of, in principle, know how vaccines work. I talked to you just briefly about this, but we don't really know how they work in great detail. So there is a lot of ambiguity within the science domain about understanding this stuff, right? And how do you convey the concept of risk? Vaccines have risk. Surgery has risks. Drugs have risk. So how do you convey relative risk? No scientist will say that something is 100% safe. Can you say truthfully to your patients, this vaccine will have no untoward side effects to your child? No, I don't think you can for most vaccines. So we as professionals, and this is a little, it's not what I do for a living, I do science, but when I get opportunities to talk to folks like you, and again, good for you guys for dedicating your lives to making people better. I care a lot about communication and how we talk to each other in respectful ways. And I think even introverted scientists who would much rather be in a dark room with a pipette and no other people around have a burden, have a responsibility to talk effectively to other people. And we suck at it. Right? So the problem with scientists, and now I'm speaking about me, not you, we, first of all, are huge geeks and no fun at parties, but more importantly, we never say never, right? So what are the chances that an orange alien is going to crash through the ceiling, speak French, and make each of us a mushroom omelet? A normal human would say no chance in hell, 0. A scientist would say p-value less than 0.00. And this becomes a problem, because if you ask a scientist, do vaccines cause autism, the scientist will say something anodyne and empty like that. The overwhelming evidence suggests that there is no link between vaccine and autism, which is unsatisfying to a parent who needs to hear the word no. So You can disagree with me. Some of you actually may be those individuals or have relatives that you care about where you believe that there is an association and link. And I don't want to be dismissive of you, I promise. But it is important because parents, even despite this report that came out in 1998, parents still, now almost 20 years later, are choosing not to vaccinate their kids. That has ramifications. So as you think about immunology, also think about how you communicate with your patients. That's where I work. That's my email. Feel free to send me notes, messages if there were things. I mean, sure, tell me you liked it. I have a long ride back home. If I ended up getting a couple of emails like, hey, that was okay, that would make me happy. But more importantly, send me emails if there were things you disagreed with, things that were confusing. I can't help you cram for your immunology test on Tuesday, but I do hope that this was a little bit helpful in putting things into some bigger picture context. So thank you guys for hanging in there with me. Off the road. Guys, have any questions? In here? I don't know if Glen's side has any questions, but I guess tough luck for them. Oh, good. Laughter test. Hey, Glen's side. Anything? All right.
Thank you.